In this video we are going to discuss some basic properties and examples of exponential growth and decay. Exponential functions are commonly used for modeling in areas like biology, chemistry, medicine, and finance. It's good to have a solid grasp on them. Here's a basic example of an exponential situation. Suppose we invest $100 in an account that pays 2% interest each month and compounds monthly. This means we would have an initial amount of 100 and a growth rate of 1.02. As we calculate how much money we have each month, we simply multiply the previous month's amount by 1.02. If we let A of t represent the amount of money in the account at month t, we have A of 0 equal 100, A of 1 is equal to 100 times 1.02, A of 2 is equal to A of 1 times 1.02, which becomes 100 times 1.0 squared. This pattern continues and we see a general formula, that A of t will be equal to 100 times 1.02 raised to the t. Notice that function only changes at discrete intervals, so it is a sequence rather than the type of function we might be used to. In the account interest rate example, we can think of each dollar as drawing more dollars to it. This is exactly how we like to think about exponential growth. For instance, if we begin with a single bacteria that doubles every second, each bacteria that emerges makes more bacteria. This is an example of exponential growth. We also see this pattern in epidemiology, where we track the spread of a virus in a population. Usually there is a patient zero who is the first person infected. If the virus is highly contagious and each person infects 3 other people, we will see exponential growth of the virus among the population. A similar dynamic is in play with the spread of a rumor. If 2 people make up a rumor, and each person who hears the rumor shares it with 4 other people, we could describe the number of people who have heard the rumor at time x by f of x is equal to 2 times 4 to the x, which is an exponential function. In a more positive example of information dynamics, we might consider the growth of scientific knowledge. As people learn more and publish more papers, each paper increases the amount of knowledge in the world. Each paper will lead to the publication of more papers, and the amount of knowledge can grow very rapidly as people learn more. However, in the real world, pure exponential growth is typically unsustainable. There will usually be a limited resource which is consumed and slows growth, or there will be an intervention by external forces that tries to slow growth. For instance, as bacteria grow, there is less space and fewer nutrients in the petri dish. Their growth rate will slow as they run out of room to grow and things to eat. In an epidemic situation, people will change their behavior as they realize that they are sick and that a crisis is emerging. If sick or potentially infected people stay home in quarantine, this should lower the amount of new infections that will occur. This principle that growth often looks exponential early, but the exponential portion doesn't last, is important in predicting future research needs. For instance, if we look at a graph of the number of articles on the English language Wikipedia starting in 2001, the trend shows a classic sign of exponential growth. This would be expected, since each article that is created had the ability to lead to new articles that needed to be created. However, looking at the data over a longer time frame, the exponential trend did not continue. Around 2009, there was an inflection point where the growth rate began to slow and the concavity of the graph changed. This data does not exhibit exponential growth. There were limiting resources, such as the amount of knowledge remaining to be added and the time and resources that Wikipedia contributors were able to focus on Wikipedia. Also, structural changes to Wikipedia such as increased editing and oversight around new articles made it so fewer new articles were being produced. Exponential curves have a very distinctive shape, that looks like a sideways J or a hockey stick. One important feature of an exponential curve is that it is monotonic, which means it either only increases or only decreases over its domain. Also, exponential growth or decay curves will always be concave up. Exponential growth curves are always concave up and increasing. However, people use the term exponential growth very imprecisely, to refer to any concave up increasing curve. For instance, the graph of x cubed for x greater than 0 is concave up and increasing, but it would not be correct to call x cubed an exponential curve. The precise definition of an exponential function is a function that has the form a times b raised to the x. In this instance, the value of a gives the initial amount of the function, when the input is equal to 0. The value of b is the growth rate. When b is greater than 1, the function is an instance of exponential growth. When b is less than 1, the function is an instance of exponential decay. As a quick reality check, let's look at whether f of x equals 10 times 1/3 raised to the x power is an example of exponential growth or decay. We could just play pattern matching, recognizing that the growth rate here is 1/3. Since 1/3 is less than 1, this would be exponential decay. We can also see that by plugging in values for x. As we plug in x equals 0, then x equals 1, then x equals 2 and compare the numbers, we can see that this exponential function is decreasing, so it must be an example of decay. While exponential growth is not typically seen in the physical world over large time scales, exponential decay is. We discuss the mathematics of exponential decay more in another video. There's another way to describe exponential functions, and this is the right definition if you are thinking in terms of the real world. An exponential process is one where the growth rate of something is proportional to the amount of something. If the amount of something is y, then the growth rate of that thing in relation to the input is the derivative dy dx. Proportional to just means multiplied by a number, so we can write this as dy dx is equal to k times y. This is an example of a differential equation, and we will say more about this in another video.